Good morning and welcome all to Day 2, Session 1 of 5-day ATAL FDP on emerging trends in Internet of Things IoT. Today also we are having 3 sessions. Again I am reminding you that you have to maintain 80% attendance. We are taking attendance digitally and through feedback also. Our day 2 first session speaker is Dr. Aftab M. Hussain, Assistant Professor, Triple IT Hyderabad. He will deliver his talk on the topic LoRaWAN devices for IoT applications. Now, I invite Professor Nidhi Dhale ma'am for the introduction of session speaker. Over
Yes,
to you, Nidhi ma'am.
yes, thank you, Mukti ma'am. Good morning, everyone. Dr. Aftab M. Hussain is currently an assistant professor at International Institute of Information Technology, Triple IT Hyderabad, and the principal investigator of the PAT IoT lab. He has earned his bachelor's degree from IIT Roorkee, MS and PhD from King Abdullah University of Science and Technology, followed by postdoctoral fellowship at Harvard University. Professor Aftab has more than 9 years of experience working with device fabrication, thin film categorization, and device testing, along with sensor applications in IoT and related areas. He has more than 80 scientific publications, holds 4 granted US patents, along with 6 others in various stages of filing. He is a member of Executive Committee, that is EXICOM, of IEEE CAS and EDS Joint Chapter in Hyderabad and Associate Editor, Flexible Electronics at Frontiers of Electronics Journal. A very warm welcome to you, sir. Thank you, Mukti ma'am. Over to you, please.
Thank you. Good morning, everyone. Thank you for that introduction. So my name is Aftab Hussain. We'll be talking about the applications of a very interesting kind of technology, which is an LPWAN technology. Particularly, we'll talk about LoRaWAN, which is a kind of an technology, and we will see how we can use it for Internet of Things applications. Can you share? Can you see my screen
Yes, sir, screen is visible.
along with the pointer?
Yes, sir.
Perfect. So we'll start with some basics. I'm sure because all of you are attending the FDP on IoT, you probably have already discussed this. But a very quick brush up on what IoT is. One of the reasons is because whenever you ask somebody what IoT is, 10 different people will give you different answers, even the experts. Um, so if you ask me what IoT is or what IoT is, I would say internet, which is the runner of IoT, is basically the interconnection of computers. Okay, and I'm saying computers in a very general sense. When I say computer, I mean everything, like laptops, computers, of course, included, but also servers, data centers, even mobile phones. I'm including in the part of computer. So anything that is a computing device connected, like we are connecting all of these together in a gigantic network across the world. We call it the internet. So information is very easy and all of those things. It runs on TCP and all. What it is that that has obviously revolutionized our lives. So we all know that very well. But what we realize is that along with connecting computers or computing devices together, it will be great if we can also connect some things to together, right? So again, exchange of information is the key here. The bedrock is exchange of information in one thing and another. So how do we connect things together is the question, and that is what the Internet of Things is, or interconnected things, or IoT is basically making sure that we are getting things now interconnected instead of computing systems interconnected. So how do we go about it? I mean, of course, we could design from scratch, looking at various things that we want to connect together, like home appliances, and security systems, industrial machines, all the way down to chairs and doors and shoes and anything else that you can see around you. If you want to connect all of these things together, you can probably imagine an entirely new network, okay, which is trying to communicate information or send and receive information from one thing to another, like the internet. Or what we have done is, because the internet already exists, we have this internet already in place. This is, you can imagine, inside this cloud is billions and billions of computers connected to our computing devices, which includes phones and laptops and everything. They are connected together, exchanging information at will. So that entire thing is now the internet. So we see that in IoT already internet exists. So our job now is much easier. As IoT engineers, all we need to do now is, if we connect our things to this system, they will automatically be in as well. Right? So all we need to do now is to make sure that we are connecting individual things, like again, their home plans, for instance. If you connect it to the internet, you're made Internet of Things, because internet is kind of the middleman in exchanging information between various things, and you can do computation and all on it as well. So at the end of the day, what we need to do is, we need to make sure that we are connecting all of these things to the internet. Okay, and then the moment we already talking about Internet of Things, because they are by definition connected together. So for instance, if you have industrial appliances connected to the internet, and also home appliances connected to the internet, you can theoretically say that there can be an exchange of information between the two, depending on protocols that are involved, and applications, and making sure that all the encryptions and keys are in place. But in theory, that is possible. Like, once everything is connected to the internet, they are also technically connected to each other. And this is the Internet of Things. The vast spectrum, this larger cloud, now can be called the Internet of Things. So, I'm going to talk about a particular technology. Like I said, it's an LPWAN technology. But where does that LPWAN technology fit in this picture? Like the big picture of IoT. It basically fits here. The black arrows that are basically taking information, say, from your shoes to the internet or back, from your chairs or from your things to the internet and to back. That is where your LPWAN technology fits in. Right? So we have to make sure that there is some wireless transmission happening at the, or reception happening at the things, and there is some gateway or some router that is connected to the internet that is receiving that information. Of course, demodulating it, parsing it, and then sending it to the application or cloud storage or wherever else you want. So at the end of the day, we have to make sure. I mean, most of the things are like, because internet already exists and is very, very optimized and sophisticated already. We have to worry about what these black arrows will be, and there are many technologies that are competing to be those black arrows. One of them is, of course, Bluetooth is a very primary technology that everybody talks about in Internet of Things. It's one of those very well established communication protocols as well. You have, of course, Wi-Fi that everybody is talking about and we have all used in our lives. And then now there is an emerging set of technologies called the LPWAN technologies, or low power wide area network technologies, that are basically trying to compete for that black arrow piece of the pie. The reason why these technologies have come up is because if you look at the reason why Bluetooth was introduced, or why Wi-Fi was introduced, it was basically introduced for wireless communication of information over a short range, very high amount of information. For instance, if you talk about Bluetooth headsets or Bluetooth speakers, they are communicating a significant amount of information, because it's digital audio information that is going from your phone, say, to your headset. That is a significant amount of information. Like it's almost like kilobytes per second, as far as I remember. So that's a decent amount of information that is being transmitted. and receive. And Bluetooth has basically been optimized for those kinds of applications where a large amount of information needs to be transmitted over a short distance. Similarly, Wi-Fi, the reason why Wi-Fi has been optimized or the way it has been optimized is very large amount of information needs to be transmitted over a reasonable, not as short as Bluetooth, but a reasonable amount of distance. Again, so that people are untethered from their Ethernet connectivity and all, Internet connection sort of in, so to say, whether you're in office or home or wherever else. That is the reason why Wi-Fi has been introduced, invented, optimized, and developed up to the level that we have right now. Both of these things, both of these technologies are great in their own right, but they have been invented for particularly very high data throughput. So a good Wi-Fi system is one that can give you a lot of throughput of data or very fast amount, or like you can get like megabytes of data per second through your Wi-Fi systems, and then multiple people can connect to it and then get a decent amount of broadband connectivity to their devices. So that's what Wi-Fi's main goal is. Its goal is not to exchange information from things to the internet, because things don't really have a lot of things to say, right? I mean, for instance, these doors, I have put this door here. Sometimes people put sensors on the door, and the information that the door is conveying to the internet is whether I am on or off, or whether I am open or not. So you will have a magnetic sensor that is attached to the door, so they are they're close together, so the door is closed. That magnetic sensor senses it and sends information to the cloud saying that look, the door is closed. When it's open, it's not able to sense that magnet, so it says it's open. So how do you convey that information? Obviously, because it's only a digital system, either it's going to be closed or open. We can say that we can convey this information literally using one bit of information, which is 0 and 1. So, for instance, you can say I'll transmit 0 if the door is closed, and I'll transmit 1 if the door is open. And then the other decision that you have to make is how often do you want to sense it? Maybe every second, right? Every second I want to check whether the door is open or not. This is a crazy amount of sampling, but let's say you want to do that. Now you have one bit of information going to the cloud every second. If you compare that to megabytes of information that Wi-Fi is capable of giving, it's a very suboptimal solution to use Wi-Fi for this kind of application, because it's like using a rocket to go to the supermarket. It's just not designed for it. It's designed for great things and much more speed and power compared to walking around and going somewhere. So because of that, this entire new range of LoRaWAN technologies have come up. So we'll go jump into that. So we are talking about LoRaWAN technologies as low power wide area technologies. They are particularly optimized for low data rate, and it's not that we like to low data rate. I mean, it's always nicer to have higher data rate, but we realize that if we reduce the data rate, we can gain on some other things. So wireless communication is always a compromise between the amount of data you can send, the distance you can send it at, and the power that you are going to use to send that information. So if you reduce the data rate consciously, you say that okay, I don't require very high data rate, let's reduce that. You will be able to gain in terms of the area that you can cover or the range that you will get, and you will basically get the battery life also much more extended. So when we talk about low power wide area networks, they are typically low data rate and low power systems, which low power is in really ridiculously low power, and as low as, I mean, when we talk about the battery life of these things, I've seen some of these devices in action. Their manufacturers claim that their battery life is close to 10 years, which is basically the life of the device itself. So you buy the device, the battery comes full charged, you never recharge it, you never change the battery. You just deploy it, it will last for 10 years, and then you have to obviously throw away the device also, because devices also have their lives. So you will basically throw away the device and the battery together. So there is no concept of recharging or changing the battery or connecting it to the grid or anything. It's just standalone system. You paste it somewhere, it lasts for 10 years, you throw it away, and you get another system. So it's a new way of thinking about electronic systems together. Of course, we have to have wide area connectivity, because again, out of the box connected solutions can be provided, so that we have to have over the air transmission, over the air activation, and all of those things, and identification of the device, along with a very large range of communication, so that we get, say, kilometers of range instead of hundreds of meters that generally Wi-Fi will provide. And of course, limit that these two capabilities or advantages come with one tiny disadvantage, that we have now limited data communication throughput, or the capability of data communication is low. So in essence, we have these LoRaWAN technologies complementing the cellular network. I talked about Bluetooth and Wi-Fi, but I didn't talk about cellular. But they also have the same problem. I mean, we are going from 2G, 3G, 4G, 5G to 6G, increasing the speed of transmission. So the bandwidth is increasing, the amount of transmission, the data throughput is going higher and higher, because you want to now stream HD videos, and you want to play video games that are very crisp and high graphics and everything on cellular networks. So we are having a larger data rate requirement, whereas Internet of Things is again very low data rate, very intermittent transmissions, and all of those things. So so these new LPWAN technologies are specifically designed for IoT, are kind of complementary to what cellular technologies do, and what short range technologies like Bluetooth and Wi-Fi generally do. Right. So, like I said, LoRa is one technology, one of the technologies in the LPWAN space. So we have this LPWAN technology that operates in the unlicensed spectrum, which is fantastic, because then you can create your own networks, your own network servers and gateways, and whatever else. So that gives you that possibility to do that. And of course, I mean, it's similar to Wi-Fi and Bluetooth as well. So they also don't have, they are also operated in unlicensed spectrum. So LoRaWAN is generally operated in unlicensed spectrum, and mostly sub-gigahertz spectrum. So we'll talk about the frequencies in a bit. It was introduced by Semtech in close to now 6 or 7 years ago, and so it's a modulation technology in itself. So it's a radio in itself. So and we'll talk about the RF of it. I mean, the technology itself, like why. So what are the advantages that LoRaWAN provides, and why it provides it in terms of pure physics? We'll talk about that. So we have to start from the modulation strategy, the frequencies, the bandwidth, and all. From there itself, they have built up this protocol, specifically again designed for low data rate and high range communication. So, and on top of it, so there is this term called LoRa, which is the modulation technique itself, or the RF, or the radio that is underlying the LoRaWAN communication protocol. So that is called just LoRa. The WAN on top of it is the wide area network. It becomes a wide area network when you connect multiple things to a particular gateway. So it becomes an entire network in itself. For that to happen, you will basically then need to have a standard protocol in place, because then if a lot of devices are connecting with the same gateway, the gateway needs to understand that these are different devices. What is the identity of each device, which means you have to have now a device unique identifier, and some encryption keys have to be there with the gateway, and some protocol has to be set in place for communication to start and stop at a particular time between different between the devices and the gateway. So this entire system then is called LoRaWAN, which is LoRaWAN is basically a standard protocol written on top of the LoRaWAN LoRa radio. Okay, so we are not talking about the actual communication protocol, including the header or the payload size, the the design of the entire system, how it will look like. So that goes into LoRaWAN. So I always give this example as if you think of LoRa as the way we produce sound from our vocal cords, like right now I'm producing. I can be producing any sounds I want, but LoRaWAN is the particular language I'm speaking in. So in this case, the English. But yeah, you can write a different protocol on top of the same LoRa modulation if you want. So that would be a kind of a, you can make it into kind of a proprietary or a secret protocol that only your devices will understand. So if you want, you can do that because there's any unlicensed. Hold on, I'm getting a call. Just a second.
Kavya? रे तू मैं आ रही हूँ काव्या, मैं तेरे को करवाने आ रही हूँ, 2 मिनट रुक जा, मेरे को मालूम है, मेरे को ही आना पड़ेगा। मम्मी को जरा सा ब्रश करवाने बोलो, रोज का ही नाटक करती है मम्मी, फिर उसके ऊपर ढोल देगी।
Okay, sorry about that. Yeah, so like I was saying that if you think of LoRa as the way we produce sounds, LoRaWAN is actually the language that we are speaking in. Now, obviously, you have to have transceivers that will be able to both receive and transmit information in LoRa modulation. But so that is one part of the system. But LoRaWAN, which is actually the entire protocol stack, that will give you benefits of standardization, which means now if you're compliant with LoRaWAN protocol and using LoRa as the radio, your devices will be able to work on any other network in the entire system. So that gives you interoperability as well. So that is one of the reasons why people have come together, and there's an alliance called LoRa Alliance that develops these compliant product services that takes care of the LoRaWAN protocol. It updates it if it feels like there's a need for updation and all of this. Right, so we are talking about this entire network. Like I said, there is this internet here, and they have all the IoT devices here that are trying to connect to the network. Using now, for instance, we'll imagine that connection methodology is our LoRaWAN technology, and people are saying that given the amount of proliferation that IoT devices are having these days, we are going to have close to 3.6 billion IoT devices by 2024. And that is an underestimate. I think it's an old estimate because right now people are talking about almost 50 billion devices by 2030, which is again staggering because there are only 8 billion humans on the earth. So you can imagine that we are basically surrounding ourselves with connected devices and IoT devices, and all of them need to be connected to the internet and in a sustainable manner as well. So this is how the network will look like. It's kind of an expanded version of what the network looks like. So this is the cloud that I'm talking about, the internet, so to say. What would happen in a LoRa network or a LoRaWAN network is that you will have your sensors and actuators here. These lines, this is the LoRa RF, okay, or the LoRaWAN communication protocol that is written on top of it, right? So from here, information is going to a gateway. Now this gateway is basically connected to the internet, right? So you can imagine this as the Wi-Fi router that we have that has that Ethernet connection plugged into it. So instead of that router, this is a gateway that is now covering kilometers of area, right? So but it has an Ethernet backhaul. So it's able to connect to the network or the internet through the TCP/IP protocol. Okay, so this part is where we want to make sure that we get it right. Right, so from the sensor to the gateway, once we get it to the gateway, we know how to do it. I mean, how to transmit information over TCP/IP anyway. So we'll be able to do that, no problem. Of course, then there is a network server that, I mean, particularly these network servers are important, particularly if you don't have a single gateway or a couple of gateways, you have hundreds of gateways, and you want interoperability between the gateways as well. I mean, like in a very similar fashion as, for instance, we have a cellular interoperability. Like we have one SIM card wherever you go. For instance, I have a geo connection, so I can go to another city or somewhere else, and then I'll still be able to get that connection over the same number. So that interoperability comes because of a very strong network server that is able to recognize devices and make sure there's no duplication of packets. There is no, if multiple towers are communicating with the same device, it should be able to parse through that information and then make sure that no duplication of information is happening, and all the devices are able to activate wherever they want and connect to the same network wherever they are discovered in that network. And if an application is requiring information from that device, they should be able to get that, forward that information to that application server. So that is what the network server does. And particularly large companies will have a very strong, very powerful dedicated network server that will be connecting to hundreds of, if not thousands of gateways across country, and getting information from these LoRaWAN devices. So we'll talk about the network providers as well. There are particularly some network providers in India, and we can set up our own network if we want, because it's an unlicensed spectrum. But we'll get into that. But what I really want to talk about today is the LoRa communication itself, like from the assets here, how information is coming to the gateway and how it's being sort of demodulated at the gateway. That is the interesting thing about LoRaWAN. I mean, the way it does is very peculiar and grants it all of the characteristics that we are talking about, the advantages that we are talking about. Right. So before I go into that, I just want to quickly give you some terminologies. This is a typical LoRaWAN stack that we are talking about. So we have this LoRaWAN MAC layer, which is basically the protocol itself that is talking about the way information is encrypted, the way information is structured, the way payload is structured, and everything else. The LoRa modulation is the physical modulation of the signal into actually the actual signals that are being produced. They are typically there in the regional ISM band, which is one of the problems with LoRaWAN technology, because different regions have different ISM bands. Some of them have a common band, I mean, particularly sub-gigahertz. Most of them have a common band in the 2.4 gigahertz and 5 gigahertz range. That is why Wi-Fi and Bluetooth works everywhere. But in the sub-gigahertz range, you have these ISM bands that are kind of separate in frequency. So, for instance, you can see in India, we have this ISM band dedicated for LoRaWAN modulation, and in the 865 to 867 megahertz range. In the rest of Asia, in China and all, it's around 430 to 433 megahertz. US is 915, EU is 433, and in some parts you can get 868 megahertz as well. So you can imagine that if there is a LoRaWAN device that has been made for the US frequencies, the entire modulation, the RF circuit and the antenna will be specifically designed for US transmission. Which is, you bring the device in India, there's a good chance it will not work. That is one of the problems that people are still working on and trying to see if we can get around it somehow. But this is one of the key problems that we are having currently with LoRaWAN technology. But given that most of the devices that we are talking about aren't very mobile in nature, I mean, why would you take your entire door to the US or vice versa, right? There are many assets, many things that are immobile in nature, that is not going to move anywhere. Home appliances are there, industrial equipment is there. So that is not going to go anywhere. So you can basically, based on the region that they are in, use the particular frequencies, and then that should basically get you going. Right. So more terminology. Sorry for LoRaWAN. I'm going to call end device node or node the thing that we are connecting to the internet. So an object that is embedded with a low power communication device is going to be called the end device or the node. The gateways are the ones that receive broadcast from the end device or send information back to the end device, right? So those are called gateways. The network server is basically the one that routes messages from the gateway to the right application and back. I mean, again, this is the diagram that I was talking about. So we had end devices at one end connecting to the gateway communicating with the network server, and the network server communicating with the application server. The unapplik message is the message from the device all the way up to the application. So it's going again from the device to the gateway to the network server to the application. And your application or your downlink is basically going from your application all the way to your device. So these are the two kinds of messages that are there. Now in LoRaWAN, what we do is when we are doing this uplink and downlink, one of the things that we try to do is we make sure that the device is not active all the time. Again, if you want to increase the battery life of a device all the way up to 5 or 10 years, you have to do a lot of optimization in terms of the battery usage. And one of the things that we realize in Internet of Things is that messages don't need to be transmitted all the time, right? For instance, I'll give a simple example of a car parking lot, right? So if we have a car parking lot and we want to figure out, say, using some sensor system, that which of the parking slots are taken, so that we can transmit that information to the cloud, and then users can see it while they're driving, that the next parking lot has so and so open parking spaces or no parking spaces are open, whatever. So we all we need to do is detect whether a car is parked at a particular parking lot or a parking lot space, and if it's occupied, we have to give, say, let's say if it's occupied, we'll say transmit a 1. If it's not occupied, we'll transmit a 0. Now, the question is, how often would you check whether the car is there or not? Right? I mean, so that is the sampling frequency that we are going to use. Now, I could argue that you can probably check it every 15 minutes. Right? So, the granularity of checking whether the car is there or not doesn't need to be every second or every 5 seconds. It's not that high frequency, change up anyway. People will take their time in parking and whatnot. So even if you check whether there is a car there or not every minute or every 5 minutes, that is going to be more than sufficient for your application. A similar example is better example for this particular thing is smart agriculture. A lot of people are talking about agriculture these days. One of the things that we will do with smart agriculture is they will plant temperature sensors and soil moisture sensors everywhere in a farm and try to see what temperature and what soil moisture they are getting at a regular interval. Now, again, I would argue, or I would ask you this question: how often do you want to sense temperature of an open area, or how often do you want to sense soil moisture of your farm? The answer to that is, even if you do it every hour, I think it's going to be okay, because temperature is not going to change suddenly from 20 degrees to minus 20 degrees in an hour. It's going to go from 20 to 19, then maybe 18, then evening comes in, so maybe 16, 15, like that, and then when sun rises, maybe higher. But even if you sample it every hour, it's more than enough. Soil moisture even changes even slowly, or in an even slower fashion. So you have to figure out that, you have to realize that if you want to conserve battery, one of the best things of doing or conserving, or one of the best ways of conserving battery is by sampling a particular environment or information, going to sleep, and then waking up and then sampling again. and then going to sleep. So you sample, you transmit information over LoRa, then your device goes to sleep. When it goes to sleep, the microcontroller is not active, the sensor is not active, and only the RTC is active, which is basically making sure that it wakes up again. Otherwise, it will never wake up. So because of that, it's consuming very low amounts of power. I mean, the currents are of the order of nanoamperes in some cases. So you're consuming very low amounts of power most of the time. So if it's an hour gap between two sensing, so for 1 hour you have almost consumed no power. Then your device wakes up, it starts consuming power for a few seconds. It senses the thing that it wants to sense, say soil moisture for instance, gets that information, transmits it to the cloud, and then goes back to sleep. The entire cycle of waking up, sensing, and transmitting can be done max to max 1 second. I mean, 1 second is a lot of time in computer in embedded systems, but let's say 1 second is the amount of time we are going to take. So in an hour, we have only consumed power for 1 second. That is that is where you can get real optimization for battery, and that is where LoRaWAN really comes in. So what it does is it basically breaks down devices into three classes: class A, class B, and class C. So what the class A device does is it supports bidirectional communication between the device and the gateway. So uplink messages that are going from the device to the network server, like through the gateway, can be sent randomly at any point. Which means what? Your device can wake up at any point it wants. It will sense the information that it wants to sense, and then transmit that information. And the gateway is, of course, is awake all the time because it's connected to the internet and it's connected to the power, like mains power and all. So the gateway is always up. So the moment your device wakes up and transmits information, the gateway will be able to pick it up. Now, in most cases, you want to have some acknowledgement of the fact that the gateway has picked up that information, which comes in the form of a downlink from the gateway to the device. So the device is saying, "This is my soil moisture," to the gateway, and the gateway is saying, "Okay, I received that information." So even that comes as a downlink, right? I mean, the acknowledgement of the fact that gateway has received something has to be sent wirelessly and has to be sent through that protocol. So LoRaWAN protocol takes care of these acknowledgements and all, so that's not a problem. But if you have a class B device, what it will do is it will transmit first and then wait for a few seconds for either that acknowledgement or some other information that the gateway really wants to tell the device. So that it will basically open up a receive window, like the device opens up two receive windows at specified times after the uplink transmission. So the transmission happens, and then it waits for a couple of windows for the downlink to happen, either in the form of acknowledgement or something else, some other information. If it doesn't respond, there is no transmission, the device goes to sleep, and so when the device goes to sleep, the gateway can now not communicate with the device at all. The only other time that the device will be able to the gateway will be able to communicate with the device is when it wakes up again, transmits something again, and then the gateway will know, okay, now the device has woken up. Now is my chance to talk to it. So these are class A kind of devices. Class B devices are extend the class A by adding a scheduled receive window apart from their wake up time. So when they wake up, they can communicate with the gateway, but sometimes there is a time synchronized window as well. So you can say that every 24 hours, so every 9 a.m. every morning, there will be a window for receiving something. So the device, whether or not it has to send something, whether or not it has its regular wake up is scheduled at that time, it has to wake up and then receive something from the gateway. So those are class B kind of devices. And class C devices are the ones that are woken up all the time, basically talking to the gateway back and forth all the time.
ED.
So those are class C kind of devices. So these devices are there. Mostly you will hear about class C because they are the ones that consume the least amount of power, and they are the ones that are specifically designed for most of the IoT applications that I'm talking about. Because honestly speaking, there's not a lot of information that needs to go from gateway to device anyway. particularly if there's a sensor system, all you want to do is get the information from there, like temperature, soil moisture, car parking information, whatever else is there. You just need information from there. Nothing really needs to go back. So we are okay from that point of view. So either that, or in some cases you can get directly Class C devices, particularly because when you are connecting it to the grid. I mean, for instance, if you have deployed energy meters, right, and smart energy meters that are on LoRaWAN communication, because they're connected to the entire grid. They're monitoring energy. There is literally infinite power. So why would you worry about optimizing battery and all of those things? So you can keep them on just in case you want to say something or transmit, say, an over-the-air update or something like that. That you can then you can if it's connected to the grid, there's a good chance it can be a Class A device. Right, coming one layer below this, we have the LoRaWAN, the LoRa modulation, and like I said, in India, you have the frequencies ranging from 865 to 867 megahertz. So they are generally divided into channels. These 2 megahertz bandwidth is divided into 8 channels of 250 kilohertz bandwidth each. So LoRaWAN systems in general, also in other countries, will have this kind of a bandwidth, either 250 kilohertz or in some cases 125 kilohertz bandwidths are allocated for a specific channel. And we'll talk about what a channel means and what that can do. And they're generally sub-gigahertz in nature. So in India, we have this range, and it's basically divided into 8 channels, most of which fall in the unlicensed region. Right. So beginning with the LoRaWAN terminology, I told you about the end node and I told you about the receiver. Now I'll tell you about something very important. It's called the link budget of transmission. That's not particularly LoRaWAN specific. It's applicable to other wireless technologies as well. But what it means is basically the amount of power that a particular signal has, right? So when you are transmitting something, it's obviously the most powerful where the transmission starts, right? So if you have your end device here, right, it's transmitted something. It's basically electromagnetic waves in the air, so photon in the air. So it's basically just going around as a wave or a particle, whatever, or both. So it's spreading through the air, and it obviously at any point in that spread, its intensity will keep weakening by the 1 by r square law. So you will get lower and lower and lower power or intensity if you go further away from the end device, right? Now, if obviously if the gateway has to receive this information as valid information, it has to have some power. Some minimum power has to be there to make sure that the gateway is able to demodulate whatever information was there in the original transmission. Now, what is the minimum power that the receiver can receive reliably? That is basically called receiver sensitivity, right? So we have at one hand the transmit power, which is decided by us, how much power we want to transmit at, and at the other hand we have receiver sensitivity, how much power needs to come to the receiver minimum so that it's able to demodulate and receive the signal reliably. So these two powers are of course far apart. I mean, this is transmission power is much higher and receive sensitivity is much lower. But the distance that your signal can travel and still be picked up reliably at the receiver really depends on that gap. Okay, so that gap from the transmit power to the receive sensitivity, this gap is basically called the link budget. Okay, so this is the link that we are establishing, the transmission link that we are establishing, and the budget is almost like energy budget is like financial budget or home budget. You can spend before you go back, kind of. So the receiver sensitivity is this line You have your transmit power here. This is free space loss, right? 1 by r square. This is going on like this. And if, for instance, if it goes like this and keeps going like this, for instance, goes below the the receive sensitivity, which is here. At this point, this is the maximum uh, coverage that you can get, or the maximum range that you can get. So this is the maximum range that you can get for your transmission. Now, obviously, if you increase that maximum range, there are two ways you can increase this. Right, you transmit with a higher power. Obviously, it will go further. No problem there. Or you reduce receive sensitivity level. So, how do you reduce sensitivity level? You basically, what that means physically is that even for very small amount of power that is received by the receiver, you should be able to demodulate the signal reliably, right? So either of these things you can do, and if you do that, you will be able to get a bigger link budget, which will give you a bigger range. The way LoRaWAN basically, or the way modulation has increased link budget and thus has become a wide area or a large, long range communication protocol is basically by making sure that the receive sensitivity is very, very low. Of the order of, in some cases, minus 150 dB receive sensitivity is what you can get. Why do you get that? We'll talk about that in a bit. But that is one of the key reasons that LoRaWAN has become very popular. Now, obviously, let me raise these things. Obviously, this is line of sight communication. What will end up happening sometimes is that you will have power going in like this, and maybe there's a brick wall here, right? So if there is a brick wall here, or a door or anything else like that, I mean, so maybe your end node is say sitting in my office, and your receiver or the gateway is outside. Obviously, the signal has to then cross one of the walls or the door. The moment it does that, it also loses a lot of power, right? So it basically goes like this, goes down, and then continues its free path loss. That obviously reduces the range that you'll get, right? So now the receiver sensitivity has hit that receive sensitivity level much faster than you would have otherwise hit it when there was no obstacle. So there's difference between obstacle and non-obstacle in wireless communication parlance. We call it line of sight communication and non-line of sight communication. So when you're talking about free space only, I mean there's only free space between the two devices, the end node and the gateway. We call it line of sight communication. Okay, and when there can be obstacles, it's indoors and all the multiple obstacles are there. Then we call it non-line of sight communication. Right. So this is all. So this is the link budget that I was talking about. It's from all the way from the transmission transmit power to the receiver sensitivity. Right. So the link budget basically provides a clue about the quality of the communication channel. It depends on the receiver sensitivity, which basically then depends on the SNR in the channel, which is the signal to noise ratio that is there in the channel. Which means if your signal is very, very clear or peculiar in nature, so noise is generally random electrostatic fluctuations that are there in free space and in nature, and because of all of our transmissions, bubbling around. So this is the general electromagnetic noise that an antenna will pick up. If your signal is distinguished from that, either because of its strength, I mean its amplitude is very high, or because its design is very peculiar, so it's easier to identify than the noise or identify among the noise, then your signal to noise ratio is high. And when your signal to noise ratio is high, your receiver sensitivity increases because you are able to detect or determine very low power signals as well, because you are able to distinguish between them and noise. So your link budget depends on the receiver sensitivity, which depends on the signal to noise ratio, which depends on the modulation that you are using. Right, and link budget in LoRaWAN can be as high as 150 dB, like I just said, which can basically give a theoretical range of 800 kilometers from a single gateway. So one gateway sitting here can communicate, I mean here as in I mean Hyderabad. So one gateway sitting in Hyderabad can communicate with an end node in Mumbai, theoretically. And I'm saying theoretically, people generally say theoretically because it's not practically possible for multiple reasons. But in this case, it's actually possible. And the world record for the longest communication, LoRaWAN based communication between two devices, I mean one device and one gateway, is 860 kilometers. That is the world record for LoRaWAN communication. So it's a very long range communication if you do it right. I mean, if all the conditions are ideal and whatnot. Current world record is 832. I think this is an old slide, so it has gone to 860 as far as I remember. Right. So what is the? So I told you that modulation is where all the magic happens to make sure the link budget is high. So what is the modulation LoRaWAN is relying on? So the LoRa modulation. So generally, legacy systems like all the other wireless systems that you will hear of either use on-off keying or mostly they'll use frequency shift keying or FSK modulation. What that means is basically you will have, say, a particular bandwidth is there. So you will have one frequency for 0 and one frequency for 1 transmission. So if you basically if you want to go 0 1 1 0 1 1 1 like any kind of digital system communicates, you will switch between one frequency and another. In the band that we are talking about, for instance, you can say hypothetically that 865 megahertz is say for 0 and 867 is for 1. Right? So you can go back and forth between these two frequencies and keep transmitting the information that you want, and the receiver obviously knows that when it receives 865 it's 0 and when it's 867 it's 1, so it will basically do modulate it and get it done. This of course is a kind of FM, like frequency modulation in general, a specific kind of FM which is the FSK, particularly for digital signals is used, so very commonly used as well. The thing that LoRaWAN does is called CSS modulation, chirp spread spectrum modulation, which provides it robustness to interference. So the signal to noise ratio is very high, and because of that, the link budget is very high, which basically means it can get long distance communication. Now CSS has actually been used. It's not a very new technology. I mean, people have used CSS since the beginning of wireless communication era. For military and space applications for decades, it has been as a proven technology. Particularly, I mean, for military and space because their criticality of communication is important. So you have to make sure something that is at a very robust signal to noise ratio is being used. So people generally use that. But LoRaWAN is one of its first commercial implementation for CSS modulation. So what does it mean? What is CSS? CSS basically uses linearly varying frequency within the entire bandwidth of the channel. So if I told you that the channel, so you have the bandwidth from 865 to 867 megahertz, that is now divided into 8 different channels, each say up to 50 kilohertz bandwidth. Now, in that bandwidth, what we'll do is we will have a signal that is linearly going from the lowest frequency to the highest frequency. Right? So, in this graph, for instance, you can see that on the x-axis we have frequency, on the y-axis we have time. So when time is, in time you will have frequencies going up, right? So frequency is going from the lower end of the bandwidth to the higher end of the bandwidth, and then coming back and then going like this, and then coming back and then going like this. So this entire thing is transmitted. So there is some transmission happening at this frequency and then at this frequency and then at this and so on. Linearly with time it changes. So the entire packet now has that linear change in frequency with time. And then, so that is when that happens, that's called an upchirp, when the frequency increases with time. When the frequency decreases linearly with time, we call it a downchirp. Right, so this is the difference between CSS and FSK. FSK would have jumped from here to here, like this end of the spectrum to this end and back very, very quickly. So you can imagine that if you're doing that jumps back and forth very quickly, you can of course you can encode a lot more information in per unit time in that FSK modulation. That you can't do with chirps. Chirps you have to go linearly up, takes its own time, which means, I mean, if this is one bit of information, so you can see that from here to here, only one bit of information is being sent out. So this much time is being taken, which again refers us back to the low data rate that LoRaWAN has. But this low data rate comes with a very good advantage, and I mean, because we are using CSS, leading to low data rate also leads to higher signal noise ratio, which means gives us better range. So obviously, if you're trying to do, I mean, if you're an engineer, you're trying to do a CSS, you would ask me what is the length from here to here and what is the distance from here to here. So what is the frequency band we're working with, and how much time I can take for going from here to here. If you have those two parameters, you will be able to design a circuit that can do this, right? So, and if I mean, so that's not a problem. So it's a solved problem for designing the circuit. All we need is the two parameters for both the bandwidth, that we have the channel bandwidth that we have, and the rate at which it's going from lowest frequency to the highest frequency, which is now we're going to call it the sweep rate. Right, so this is how it will look. I mean, if you zoom in, your single upchirp will look like this. So this will be the sweep rate that you will have, and this is the bandwidth that you have. Bandwidth is generally of the order of 500, 250 or 125 kilohertz. It's the higher the better, of course. I mean, you have more bandwidth, you can differentiate your signal more. I mean, which means your signal to noise ratio will be even higher, because you can say one is starting at much lower band and going up to much higher band. That will give you a lot of room to make sure that your signal is received reliably at the receiver. The problem is it's a scarce resource, because you have only a specific amount of bandwidth that is available, say 2 megahertz. So from 2 megahertz, you are able to now, let's say we have divided in 8 channels, so 250 kilohertz. So it's already very short. I mean, the amount of bandwidth that you have for the entire nation and for an entire region is not a lot. So you can't expect us to consume all of that bandwidth for a single channel, and then the number of devices that can connect to it will to the network will obviously decrease. So it's a scarce resource, but higher is better. Now, the sweep rate, if you have a higher sweep rate, you will be able to decode better. I mean, higher sweep rate as in if you have a much higher time that is taking from going from upchirp from one frequency to another. So upchirp is taking a lot more time. Then you will be able to decode it better, which means your signal to noise ratio will be better, which means you will get better range. Right, receive sensitivity will be higher, you get a better range. But if you take a lot of time to go to do only one chirp, obviously you will not be able to decode a lot of or encode a lot of information in it. So your data rate will decrease. So there is this trade-off between the data rate and the range that you can get out of LoRaWAN. Now, if you use this, what we can eventually do is you can have these kinds of chirps that are either complete or intermittently stopping somewhere, and then your entire signal or your packet that now needs to be sent will basically look like this in the frequency domain. So this is time, this is frequency. In the time domain, it will look like this. So the frequency is changing kind of linearly or haphazardly. So very difficult to figure it out from human eyes. But in frequency domain, this is how it will look. Now, what you'll do is once you have done this modulation and transmitted, at the receiver end, what you'll do is obviously you receive this signal. You will then basically multiply it with an inverse term. So your frequency addition basically is what you're doing when you're doing signal multiplication. So you will have these signal mixers that will basically add these frequencies together, an inverse chirp from this side and an up or down chirp coming from here. And when they get added, you will realize that you will get very specific decoded symbols for if there is a discontinuity anywhere in the chart. This is where the information has been encoded by the transceiver, by the transmitter. Right? So when you do that, you will basically get very, very distinct levels of signal. Now, obviously, you can imagine, you can pepper all of these things with random noise. Random noise that is basically a particular frequency here, here, or here, with a specific amplitude and all. It's randomly generated packets of signal or packets of noise in the electromagnetic spectrum. If you multiply that with the inverse chirp, they are not going to give you a specific decoded symbol. They are going to be garbled values. So, because of that, what ends up happening is that your signal to noise ratio is extremely powerful because of the CSS protocol and the inverse chirp that we are using. So once we have these decoded symbols in place, the receiver knows that these are actual symbols. They can't be from noise. I mean, it's very hard to generate noise that would give you this kind of signal. The probability of generating that is extremely low. So you can get symbols decoded for very, very low power received at the receiver end. Like I said, 150, minus 150 dBm and all. This is a staggeringly low amount of power. So this is the power of LoRaWAN and LoRa modulation. So because it's relying on CSS, it gives you higher signal to noise ratio, it gives you better link budget, which gives you a long range of communication. But the only thing that you are sacrificing here is because you are going for all of these long and time delayed up chirps and down chirps, you don't have a lot of data rate that can be transmitted. But that is okay because, like we discussed earlier, IoT applications don't really require a lot of data rate. Right, of the order of 1 byte per second, is more than enough for most of the applications that come to my mind. And LoRaWAN can provide that, so that's not a problem. Right. So it basically comes down to the three things that we are discussing here: the transmission power, the bandwidth, and the spreading factor. The bandwidth is, like I said, the width of the band that we are using. This is the channel plan that you have. Transmission power is of course in your hands because you have made the device. You can transmit at a specific power. Obviously, if you go at a higher power, you will get a good transmission and you will get a reliable transmission, but your battery will run out quickly. So you have to make sure that the transmit power you are choosing is appropriate for both the battery to be lasting as much as you want, as well as the transmission to take place. The spreading factor is basically that relates to the amount of time it takes from to go from from low frequency to high frequency, like one chirp, how much time it's taking. That is what the spreading factor indicates. So that is again one of the things that is in your hands, because when you're designing the transmitter, you can design it for a specific spreading factor and encode that spreading factor in the LoRaWAN stack itself. So if you lower the transmission power, you will save battery, but the range will go down. And if there are obstacles in the path, again, there will be a problem. So they have to, all of these three norms, they have to make sure that they are set at a particular point to be able to get a particular range, a particular signal to noise ratio, a particular battery capacity. The bandwidth is the width of the channel. I mean, we have already discussed this. They combine, and the spreading factor corresponds to the amount of time it takes for a chirp. They combine to form the data rate. Obviously, I mean, larger bandwidth and smaller time, larger bandwidth and larger time will give you the same amount of this thing I'm scaling up together. If you have a smaller time and smaller bandwidth, it will go faster. So that will basically give you how fast, you're able to, what is your data rate. Now, obviously, if you go for a smaller bandwidth and lower, sweep rate, your signal to noise ratio will be worse. So you'll get a good data rate, but your receiver sensitivity will become bad. So again, all of these optimizations and trade-offs are there everywhere you look in the wireless spectrum. So this is the configuration of the spreading factors and data rate for the Indian channel plan. So for instance, SF7 is the one that gives you the highest data rate, right? Because the lowest spreading factor. And as you go higher in spreading factor, you will basically be able to get lower data rate, but then the range of transmission will increase because your signal to noise ratio or receive sensitivity is higher. SF7 is the shortest time on air, SF12 is the longest. And each step in the sprint actually basically doubles so it's an exponential growth. So it's not a linear like from 7 to 8 and 9, it's exponential growth. LoRaWAN uses a different configuration of frequencies, spreading factors, and bandwidths depending on where you are in the world. So for India, the channel plan is again from 865 to 865 megahertz. Right, so this was all about the LoRa modulation, the spreading factor, the bandwidth, and everything else. If you look at the protocol, the LoRaWAN protocol, like I told you, it will have something more than the modulation. It will depend on the modulation, but then on top of the modulation, you have to write an entire actual protocol or the language that you are communicating with. So you will have this kind of an entire message, which will have only a part of it as the payload, right? But most of it will have things like the preamble, where it's like the moment the gateway receives the preamble, it knows that the communication has taken place and so on. You will have a header, you will have information about the device, you will have information about the encoding, you will have information about the encryption, you will have information about the device ID, and all the other things that are there, apart from the actual payload that needs to be transmitted. So sometimes it ends up happening. This is how life works. For transmitting something as small as one bit of information, like 0 or 1, your entire payload or the entire message will be of the order of a few bytes. Sometimes tens of bytes or hundreds of bytes for just transmitting one information.
Excuse me, sir.
Yeah.
There are a few questions related to LoRa modulation. The first question is from Rajkumar Jaswal. That which particular tool is required to simulate the LoRa technology?
So it depends on what you're trying to simulate. If you're trying to simulate the circuits that are involved here, you can go for things like cadence. Will give you if you're doing RF and all of those things, circuit designing, probably cadence will give the answers. If you're looking at a slightly a deeper level of the way antenna design needs to work, then probably answers will give you the answer to most of these things. So there are dedicated tools, both for either for RF or for circuit designing. And if you want to go slightly higher up on the order, you can. If you want to, for instance, make your own devices or end nodes using communication, you can get them off the shelf. So for instance, you can get LoRaWAN based radios, transceivers that are freely available. Online you can just buy them. So and then you can communicate over UART with these radios, and then receive them as well. So you can form a peer-to-peer network from using LoRaWAN. So and again the code for that, is very very simple. You can literally use an Arduino, use a UX like the UART communication from Arduino with these LoRa radios, and send information to another radio, something like that. So all levels of abstraction, you will be able to find some tools or the other to work with.
Okay, thank you, sir. Next question is it possible in MATLAB?
What do you want to simulate exactly?
Uh,
I mean, there are things. I mean, simulate can simulate the data flow, I guess, work, particularly from the gateway to the network server to the application. But if you want to do something really physical, I mean, modulation related things, I'm not sure if MATLAB is the way to go for that.
okay. So next question is, does it deal efficiently for huge amount of data?
Depends on what you. So the LoRaWAN packet size is restricted to 51. So that's this is a good time to ask this question because so we're talking about this packet, the payload size that is there along with the header and everything else. The actual payload that is there for one transmission of LoRaWAN information is restricted to 56 bytes. Okay, I think it's 51 or 56. I'm forgetting, but probably 56 bytes. So 56 bytes is all you get, right, for transmitting something. Now, obviously, you can say that I can transmit, 56 bytes at a time and then stick it that information at the network server end. You can do that, but again, it's not
बबलू
designed
से
for
दूध
it.
पी
I mean,
लिया
it's
क्या?
not. If you're transmitting, for instance, an image or a movie or a video file or an audio file, you can imagine that 56 bytes is nothing, right? What is the size of your images these days? I mean, if you take a good image from a phone of the order of 2 megabytes, 3 megabytes, 4 megabytes is the image size that we are getting these days. How much time it will take for you to transmit them 56 bytes at a time? You probably need like 1 million transmission, right? 100,000 transmissions. You can do that, but it's again not designed for it. It's designed for something that is extremely low data rate. For instance, car parking, whether car is there or not, 1 bit information. Whether door is open or not, 1 bit information. Temperature, 2 bytes of information. Humidity, 2 bytes of information. Air quality, 2 bytes of information. Whether a motor is on or off, 1 bit of information. What is the current being consumed? Again, 2 bits of information. I'll give you an example though, like when we come to the applications, I'll give you a very interesting example that we are actually currently working on. We're writing a paper on that as well, on the size, the design of these packets for some large, applications. So we'll come to that in a bit. But even in that case, I'll tell you that the application that we're working on is still sensor based. It's not high data rate at all. I mean, so if you're trying to stream a movie, LoRaWAN is definitely not the way to go.
Thank you, sir. Next question is from Murli Anantha. Are LoRa implementations available for use from any service provider?
So can I take that later? Because we're going to talk about applications now. So if we, I mean, we are done with the technology part. We'll talk about some example applications. I'll definitely very happily take up this question there.
Oh, okay, sir. Fine.
Right. So this brings us all the way back to the same diagram that we had seen first. So we have this. Now you basically, hopefully, understand to some degree of depth how LoRaWAN is basically transmitting, like generating that CSS chirps here. It's getting transmitted through the air. It gets dissipated, but there's still enough power left when it hits the gateway. It's able to demodulate it, get the information out. Once the information is out, you can transmit it over the internet to the network server, and the network server knows where to store it and what to do with it. So this is your entire LoRaWAN network. Now, the network providers, I think somebody was just talking about that. So this network server and then the gateway, I mean, it looks very close to the LTE networks that we have, the 4G network or the cellular network, phone network that we have. Right, so in terms of if I give you this diagram for phones, the same thing is their cell towers are here, your individual mobile phones are here, the cell towers are connected to the internet, I mean, so that they can fetch information from YouTube and wherever else, games and whatnot, and then provide it to your phone, communicate it to your phone. That's what's happening. The next question you will ask me, sir, okay, that is great, but who is providing this network? Who is the network provider? Then I'll tell you Airtel is there, Jio is there, and Vodafone is there. You can go to them, get their SIM card, and that's how you connect. So in terms of LoRaWAN, how do you get the network? These are the network providers. Tata Telecommunications, of course, provides a network of LoRaWAN across India. There is a sort of a startup called Sendra, which is based out of Delhi, which also provides network connectivity in many cities in India. Yeah, and there is a community called the Things Network. It's a very interesting thing in itself, which basically provides not a network, a network server. So what they do is they say that you buy your own gateway, like you buy a Wi-Fi router, connect it to our network. I mean, they'll give you an entire like a script and what not to basically encode in or burn on the gateway firmware, which will basically, in essence, make it their gateway, right? So it's your gateway, but now you've connected it to their network server, which means anything that is communicating with your gateway that information can now be seen on their website, right? So and it's all public information, so you have to be careful what you're connecting. But it was supposed to be a very small initiative by a couple of people, like again a garage startup story from Amsterdam. They realized that okay, this LoRaWAN thing is kind of cool, so they bought their own gateway and put it on top of their home, and then just floated a website saying that look, if you want to connect to this network server, you are free to do it. And in a few weeks, months, years, first started with Amsterdam and then all of Europe and then all of the world basically connected to the network. So you can Google the Things Network. The story is incredible, but you will find there's a good chance you'll find their network somewhere in your locality or vicinity, just because so it's a crowdsourced network. If some enthusiastic person, I'm also hoping that you will be one of those people, has bought their gateways, connected it to the Things Network, and then the entire area around that gateway, which is like a few square kilometers, suddenly any LoRaWAN device can directly communicate with the Things Network across the world. So it's a very interesting initiative. It was an initiative first, now it's an entire community, industry, everything. Like they have massive conferences called the Things Conference, where they invite people. The first Things Conference outside of Amsterdam actually happened in Hyderabad, in India. And I was one of the invitees there. So it's a very large community now, but they're doing very interesting work. So we also have a gateway in our institute that is connected to the Things Network. So any device in this area can connect to the Things Network directly. You can also have Sendra and Tata Telecommunications are more commercial entities. So you have to, just like you have to buy a SIM card and then pay for the subscription. You have to basically pay for the subscription of these two entities, because they are installing their own gateways everywhere, and they of course maintain a quality of service that may or may not be there with the Things Network, because it's free and everything else. So some people will put their gateways, it will stay there for a year, then they'll take it off. You can't do anything about it. So that gateway that you are relying on for your experiment suddenly vanishes sometimes. So things happen, but that's how free things are. So either of these entities you can use in India for your LoRaWAN applications. And they are this part of it. I mean, the gateway network server part, sensors you have to make, applications you have to make. Applications in IoT. So now we'll talk about the good stuff, the interesting stuff. So, of course, variables is one big area. The general applications, we are talking about variables. LoRaWAN technology can be used for many applications in variable technologies, because again they're used for connecting sensors and connecting things together. So if you have your heart rate monitors, your BP monitors, your oximeters these days, and or anything else. You can connect through LoRaWAN to the internet, and then you can see information over time or and so on, and then get useful information from there. Obviously, low power communication means that the battery lives forever, or the battery lives are very high, which means in some cases people are also seeing if you can implant something under your skin or in your body, and if the battery lasts as long as the implantation lasts, that will be fantastic, because then you don't have to worry about ways of recharging it and whatnot. So there's no need for recharging and changing of the battery. Of course, other general applications include remote sensing, which we have been talking about. Like you have large fields, you just put temperature sensor anywhere, and I've seen these temperature sensors. Sometimes they come in the form of like a sealed device, because you don't have to change the battery, you don't have to recharge it. So there's no port for recharging. There's no port for opening up anything. It's just completely it's a box that comes. All you need to do is switch it on and then throw it somewhere, and it will sense temperature and give information on LoRaWAN for the rest of its life, which is like a 10-year lifetime. So again, for soil moisture, you can do the same thing and literally bury it so that this is the antenna is coming out. Everything else is buried underground forever, and it will just keep giving soil moisture information. So these things that don't rely on battery technology, or I mean are not very battery heavy, actually are opening up an entire genre of devices, or this entire field of devices that are very specific, very interesting electronic devices. Parking sensors, we just talked about the parking. I've seen one parking sensor on LoRaWAN, which was so interesting. I mean, it was like this thick, very hardy shell. I mean, again, no way of removing anything. It's completely sealed, batteries inside, it's fully charged once they give you. What we need to do with that is you basically bury it inside the road, right? So you bury it first, like in underground, and then on top of it you make the road. So you will not see where the sensor is, but the sensor is there. It's transmitting over LoRaWAN. It's basically sensing through magnetic sensing whether there is a car on top of it or not. But it's such a beautiful piece of infrastructure. You just never see it. It's almost non-existent, but it's still working and it's doing its thing. Works for 5-10 years, and then obviously in 10 years there's a good chance you'll repave the road anyway. So you will basically remove everything, repave the road. So people are actually deploying these sensors. I know of one pilot project in Chandigarh, which Sandra Co is doing with these parking sensors. Very interesting concept. And of course, smart garbage cans, because why not? One of the things that people are doing these days, and again, people are piloting these things across India. One of the things that one of the things municipalities always have a trouble with is they don't know when the garbage cans are full. So there's only one we are solving it right now. Is that there's a van that goes around and sees whether they're full or not. If they're full, they'll take them. If they're not, they'll not. But because of that manual thing, what ends up happening is obviously they don't have enough people on board to check every locality, every can. So what ends up happening is either you have to call them saying, "Hey, full okay, please take it away," or if it's in their route or in their round, it will get cleared. But what they are thinking is if they can come up with these trash cans that can transmit information whether or not they are full or not. Right, so it's only one big information, 1 or 0. So if it's 1, it's full. So at the central command interface at the municipality level, for smart cities in particular, you will have one dashboard that will say if these garbage cans are full. You can run an algorithm on top of it, and then you will say, okay, why don't we have a route of our truck going like this? Or if there are 15 trucks, one should go like this, one should go like this, one should go like this, and so on. The algorithm will tell you everything, and all you need to do is early morning get that information and then go on the route. So that will ease the life of our municipality workers. It will make their life less stressful. It will make our life cleaner because now our garbage cans will not be full all the time, and a lot of very nice things will happen with it. So people have come up with these applications already and deploying them in various places. So these were general applications that I've heard of when I talk to my collaborators, when I talk to my peers in the LoRaWAN network community. I hear about these applications. So they're general applications, but specific applications that we have worked on in IIIT Hyderabad. We have a smart campus project which is being funded by MIT and the Smart City Mission of Government of India. And under that mission, we have the mandate for putting up all of these sensors and actuators in place so that different algorithms, like I was saying, this garbage can algorithm, all of these algorithms can be implemented. So one of the things that we did is basically we have the like I was saying, the smart campus project. We are trying to completely wire the institute with sensors and actuators and monitor things like air quality, water quality, power consumption, power generation, all of those things. And we are dashboarding all of this to a central command room, which will be able to see everything and then correlate them. Like for instance, if weather is so and so, maybe how much AC was consumed. If more water was consumed, was less power consumed. All of those cross correlations can be very interesting as well. So we are making this first living lab of India in IIIT Hyderabad, where we can make this data available for analysis for other companies, right? So give them a subscription of the data so that they can run their algorithms and figure out some more smart solutions for deployment in smart cities. For instance, one application or one thing that we did is basically the smart meter application, smart energy meter. So we have the network from Centraco for this and the things network as well. So both the networks are there on campus already. And we have smart energy meters deployed on the Centra network. A total of 80 energy meters provide data every 15 minutes of the voltage, current, and power factor frequency, and the actual energy like the kWh and kVh of the entire meter is provided over LoRaWAN. Now, like I was saying, this engineering of this data packet is very interesting. We have 56 bytes of information that can be sent over one transmission. So we have two options: either we increase the number of transmissions and send a decent amount of information, whatever information we want, or we compress, squeeze the information into 56 bytes. So what we ended up doing is that in one packet itself, like 56 byte itself, we were able to transmit all the necessary information that was there from the meter, which includes, it's a three-phase meter, so it includes red voltage, red phase voltage, blue phase voltage, yellow phase voltage, all of the three-phase currents, the power factor, the frequency, the kWh and the kVah, like the lag and the lead for the power being consumed. So all of those things we have compressed it into a 56 byte information, basically saying of the payload, the first two bytes are corresponding to red voltage, assuming the next two for blue voltage, next two for yellow phase voltage, and then we have current information packed across, and then we have voltage, the power factor and all of those things squeezed into 56 bytes of packet. So this basically is transmitted, so the meter reads all of those things, constructs the packet according to the information that is provided, sends that packet over LoRa. At the gateway, the packet is received, decrypted, and forwarded to a particular network server or particular intermediate server that is specifically decoupling all of this information. Right, so that 56 byte of information now needs to be separated out and figured out from there what is the voltage, what is the actual current, what is in terms of voltages and amperes and all of this. So it's a very interesting problem. We are actually currently writing a paper about it to be submitted shortly. So it's a very interesting problem that was solved designed in a particular way. So once we do that, we are also using the 1M2M implementation at the data level to be able to store all this information as well in a more synchronized fashion. So very interesting project this. Another project that we have done with LoRaWAN is the Indore range as well. I mean, we have tested peer-to-peer LoRa devices with transmission of 23 dBm and received sensitivity of minus 140 dBm to see how much range we can get. So we're able to get line of sight communication all the way to 3 kilometers, for instance. But normal line of sight or indoor structures have a very interesting or peculiar design of them in and of themselves. So we have to make sure that we also study the behavior of LoRaWAN communication indoors, because sensors can be indoor and the gateway can be outdoor. So it has to cross a wall, that signal has to cross a door or a wall or something to get to the other side. So it's very important that we do these kinds of studies. And this is not the first studies that was done in India, because I mean there have been LoRaWAN indoor studies, but not in India. And this was important because we stated that because the building construction material is different in India. I mean the way we construct our buildings is different from what they would do in the US, UK, South Korea, and all. So we have to make sure that we do these studies specifically for our Indian buildings. So what we did is we basically put a gateway. This is where my lab is. This is the floor plan of the institute, third floor. We put a gateway here, and then we looked at the RSSI value, which is the received the relative signal strength index that we get for different points in the building. So obviously, as we go away from the gateway, you can see that the RSSI values are reducing. So particularly we had this long stretch of corridor around 100 meters or so. So we looked at how signal is propagating from there. We looked at if you go from one room to another, which means the signal has to now cross a wall. What happens, like if you have multiple walls, what happens, all of those things. We looked at all of those things. We looked at information like, for instance, if there is a window or a multipath between the signal and the transmission and the reception, then what happens. So at the end of the day, it became a very interesting study. We had to publish it in a recent conference that happened in Pune called I2CT. We had all of this, for instance, RSI values for rooms. So this is the room where the gateway is. The room that was right next to it, because of the wall, there is a significant decline there, and then you have some more decline because of subsequent walls that we have. And then we actually did the entire study for the campus itself. I mean, so we kept the gateway here. Somewhere here is where the gateway was, and then we looked at what kind of reception we are getting across the campus just from the single small gateway. It's not even professional, like it's not an outdoor gateway. So very small. I mean, very you can buy it for like 50,000 or not very expensive. So we were able to get this like high signals around it, and then as we go away from it, we get lower and lower signal strength. This was this is the entire campus, Triple IT campus. I think this is on the order of half a kilometer square. So very interesting information was obtained, because the gateway right now is indoor and the mode is outdoor. I mean, you can switch it, it's the same thing. But if you're trying to do any communication that has, say, real life implications, like as trees, as buildings, as structures, as people walking around, you have to make sure that this kind of information, this kind of studies are done more and more, so that we get information about what is the actual or the real life, real world scenario range that LoRaWAN can provide. It can clearly provide in the order of kilometers, even real life, even with a small gateway, insignificant gateway, indoors with multiple structures and everything else, you can still get off the order of half a kilometer or a kilometer. If you do it right with line of sight communication, you can go all the way up to 10 kilometers. I mean, there was this project for a company that we did. That project, we were able to get something like 3 kilometer line of sight range. And it was very hard to test, because where are we going to test 3 kilometer line of sight? So they had to go all the way out to, there is a ring road called Outer Ring Road in Hyderabad. So the outskirts of Hyderabad, then they had to basically park a car and then go in a car and then see, okay, how much range you are getting. line of sight. So it's testing itself is a hard problem. It's not easy to solve. But you can get all of this information very interesting. Studies can be done, and these studies are important. I would urge all of you to do these kind of studies in your local colleges and institutes. They're very good papers to write as well, and you can get very good recognition for the work that you are doing. Yeah, so that is all I have for today's discussion. If you have any questions and comments, please let me know.
It's a question from are LoRa implementations available for use from any service provider?
Yeah, so the way service providers work is like, for instance, I told you this example of Centraco. So if they have their network somewhere in your vicinity, the way you can find it out is go to their website and see what their network coverage looks like. So if that is true, you can buy off-the-shelf LoRaWAN devices and port to their network. The way you will port it to their network is you will have to tell the Centra network that you have to look for this device. So all the devices, all LoRaWAN devices have a specific dev UI, device unique identifier number associated with. Similar to the MAC address that is there with other wireless or wired communication or with internet, you have the IP and the MAC addresses, right? So we have this dev UI, which is a unique identifier for the device. You register that device with the network server. The network server will automatically start looking for it. As soon as the device is switched on and it's in the vicinity of the connection, you will be able to see information that it's transmitting on the Sendra port. Similarly, for the things network as well, if you have your things network connectivity around you, if you don't know whether that is true or not, go to their website, you will see their network coverage. And then if you get a LoRaWAN device, you have to then register that dev UI with the things network server. And once you do that, again, you will be able to get over-the-air activation for those devices. Obviously, if you have neither of those things, what you can do is you can make your own network. For instance, like I suggested, you can buy an LoRaWAN gateway from. There are multiple vendors like Curlink is there, and these devices you can buy and then you can port your own gateway to the Things network, for instance. And then once you do that, you have your own Things network ready. Then you can buy LoRaWAN devices and then communicate with them. So they are available. You can just go to Amazon and all. Many LoRaWAN based devices are already available on them.
Okay. So next question is how to implement LoRa based application by students at their own college.
So the way I would suggest you do it is there are LoRaWAN radios that are available. So they are not. So you don't have to worry about the Sendra network or the Things network or the Tata network. What you can do is you can do peer-to-peer communication. Peer-to-peer LoRaWAN communication is very similar to how we do hotspot on our mobile phone, right? So if you want to communicate something from one Wi-Fi device to another, one of the ways is you connect to the internet and then you can communicate information. But you can communicate information without connecting to the internet. You can just directly communicate information across two devices. So that is basically peer-to-peer LoRaWAN network. It's not LoRaWAN because you're not doing that protocol thing anymore. It's just LoRa communication. But it's a very interesting study for students. So for that also devices are available. You can buy them off many of these companies are there like Rubo.in and the component websites are there. So you can DigiKey is there. You can go and buy these radios that are available. Make sure they are for Indian frequencies. And once you do that, you can then program them to send something. So So we just use an Arduino, for instance, and send something to that radio. That radio will transmit it to the next, or transmit it everywhere. If there is a receiver in that vicinity, that receiver will get that information and then communicate that. So this is fairly easy to do.
Okay, thank you, sir. So next question is, what are the indicative cost of device, gateway, network, etc. for implementing LoRa-based solution?
Right. So if you look at the gateways themselves, they're expensive, of the order of 50,000 rupees. You will have to you will get one gateway. If you don't have any network in your institute, there is a good chance you'll have to buy that. But if you're going to do peer-to-peer communication only, I mean only through the LoRa radio, not through the LoRaWAN network, then it becomes very cost effective. I mean, for instance, of the order of, I mean, individual radios will be available for the order of 1,000, 2,000 rupees. Right, so you can do, you can buy these radios, and I mean, you have to buy obviously two at least to do one, for communication. So the entire setup from Arduino or some sensor communicating with Arduino communicating with the LoRaWAN transceiver, and then on the other side, the reception happening, and then say you're displaying it on a system. The entire thing can be done in like 5,000 rupees max.
So next question is, online tools to study to work with LoRa and IoT simulation.
Sorry?
Online tools to study to work with LoRa and IoT simulation. Is there any online tool available?
So I'm not sure what you mean by IoT and LoRaWAN simulation. What you can do is you will have to know about things like the IDs for programming all of these systems. So Arduino ID and all you can use. You can use other. I mean, if you're using multi-text systems, you can use mbed.org. All of these online tools are there for programming or embedded coding of these things, but they're generally mostly physical in nature. Can't really. I'm not sure if what value addition will be there for simulating these things. So its value. I mean, LoRaWAN's key value will. I mean, particularly at the stage of development it is in, it will be very nice if we can develop more and more hardware solutions, for various implementations. As far as software is concerned or simulation is concerned, we do have some. I mean, people do some simulations, but they're generally mathematics-based simulations. Like for instance, we have a paper in the and a patent as well on localization of assets using LoRaWAN. Right. So when we talk about localization, we generally talk about GPS or GNSS based technologies, but can we use LoRaWAN or large network of LoRa gateways for tracking of assets? So when we do that kind of things, we can first simulate it, make sure to see what kind of detailing we will need in terms of the time synchronization of the gateways, of the fact that we have to the mathematics of it. I mean, you write an equation. I mean, you say that okay, this is how the system is. Now, once you know the system, you can write an equation governing the transmission, reception, and everything else, the time of flight of the system. So once you write that equation, then you can use MATLAB to solve it. So in that paper, we have used MATLAB to quote unquote simulate the system, but we are not really simulating a system. We're just simulating a bunch of equations. That's what MATLAB does.
Okay. So anyone else want to ask some question? Yes, sir. In chat, you can see that all the participants are giving that very informative session. So thank you so much, sir.
Thank you.
Yes, sir. Now I invite Professor Meenakshi Haldar for vote of thanks.
Thank you, Professor Murthy Avadia. I thank Professor Aftab and Hussain for this wonderful and knowledgeable session. The speaker started with IoT definition, followed by low power WAN technology with key characteristics like battery life, connectivity, throughput, capacity. He gave an introduction of LoRa, LoRa network, LoRa stack, LoRa terminology. Then he started with the detailing of N device classes, class A, class B, class C. Very nice explanation of the link budget of LoRa. Then he told about LoRa modulation technique in detail. Also added LoRaWAN protocol. Applications in IoT in general are wearable devices, remote sensing, parking sensors, smart garbage cans, etc. Also gave some specific applications which was implemented in IIT Hyderabad as Smart Campus Project. Smart energy meter, Indore range. I thank Sir for this informative session. In future, we will communicate to you for such type of sessions. Hope this will help participants in their research. Thank you, sir. Thank you, ma'am.
Sir, can I ask one more question, because in the chat we are having another question?
Sure.
Yeah. So, difference between Zigbee and LoRa.
So it's an entirely different protocol. I mean, so there are multiple, emerging technologies that are coming up. Zigbee is one of them. It's so again you have to look at why these things are have been designed. It's always nice to study some of the history of technology to realize the reason why people came up with new technologies. So Zigbee was specifically designed for home automation and those kinds of networks that are slightly larger range compared to Bluetooth and wireless, and low data rate. Because again, when you're automating your air conditioning or connecting your fridge and washing machine and everything else together, there is a good chance you'll not be exchanging too much information. So it is also low power, large range protocol, but generally, I mean, it's again been designed specifically for a particular application. In home automation, people are using it like its meshes for other things as well. But yeah, I mean, LoRaWAN is again one of those things that people have designed. It has lower data rate compared to what Zigbee can provide. So the packet sizes are even smaller, the range is even larger, and the power is even lower. But yeah, I mean, there are other competing technologies for LoRaWAN as well. I mean, NB-IoT is there, which is also gaining a lot of traction these days. So multiple technologies are there. People are talking about RF mesh as one of the technologies. So it's just one of those large, I mean, range of technologies that are out there.
Yeah, okay. Thank you so much, sir. Thank you once again. Thank you, Dr. Aftab M. Hussain, sir, for your informative and knowledgeable session.
Thank you so much.
Thank you, sir. So now we will end our session, and we will meet at 12:30 p.m. On the same link for our second session. Sir, also participants want PPT from you. Can you please share us?
Yeah, I will email the PPT to you.
Yeah.
I mean on the email that we have been communicating.
Yes.
And yeah, and then you can share. Yeah.
Okay. Thank you, sir.